We're going to solve systems of linear equations by substitution. Now, we looked at how it looks when you graph, and graphing's not very accurate, so that's not really the method we want to use, but graphing is nice because it gives you an idea of what it looks like. So real quick, you have two lines that maybe cross, and the points 2, 1 is the answer. Or you have two lines that are parallel, and the answer is no solution. Or you secretly have two lines and they're the same, and the answer would be the equation. Now we want to explore each one of these. We have two different methods for doing this. The first one is substitution. And what we're going to do is we're going to assume that something like this is going to happen. We're going to be able to find an x, find a y, we're going to answer it in an ordered pair. So we're going to use what's called substitution in this problem, and it's easy to do substitution because one equation is already set up. It's solved for one variable. Let's keep track of these equations. I'm going to call them 1 and 2. So this x, whatever number it is, it's the same number that this x is. These are the exact same. That's like me saying, I have a child named Zoe, and you go, oh, my daughter's named Zoe too. And then someone else says, well, what's your daughter's name? And it's the same as her daughter's name. Well, what is that? It's Zoe. So this x is the same as this x, this y is the same as this y, because we assume the lines will cross at exactly one point. We'll explore when they don't, but in this case, they do. Pretty sure anyway. Let's see. Now, what I've done is I boxed in the left-hand side of equation number 2. And we're going to substitute or replace the x in equation 1 with this stuff. Because this x is equal to this, which is equal to this. Right? It's that my daughter's Zoe, your daughter's Zoe. There's someone else asks, what's my daughter's name? And they only know you. Well, it's the same as mine. Right? That was a little confusing, but you got the idea. It's sort of a chain of events. This one equals this one equals this one. We substitute equation 2 into equation 1. So my notation for that is 2 into 1. And it looks like this. This is now replaced with 3y minus 16 minus 4y equals negative 25. Now let me move to the side and you can see that. So what we have done is substituted. I'm going to put this in a green box. Squeak, squeak, squeak. That 3y minus 16 is now in place of the x. That's the substitution. But now what we have is a linear equation with one variable. We can solve that, then plug it back in to find the other variable. So we'll do that here somewhat fast because you should be good at this. 5 times 3 is 15. 5 times 16 is 75 plus 5 is 80 minus 4y equals negative 25. Like terms are 11y minus 80 equals negative 25. Add the 80. I'm going to move up here. What I have is 11y equals 80 minus 25. 55. This is looking good. Divide the 11 out, and I have the first variable. Okay, you are not done. Common mistake is students are like, woohoo, because you're so used to getting to the bottom of a problem where it says like x equals something, then you box it in and you move on. But think about the big picture. These are lines. These are systems of linear equations. They're lines. Your intersection is a point, not a dot, not a singleton. It needs to be an ordered pair. So what do? We take this y equals 5, and we can put it back in here or here. Now I choose to put it into equation number 2. So y equals 5 into equation 2. So 3 times 5 minus 16 equals x. 15 minus 16 equals negative 1. Now, don't make the reader is me, the grader, or anyone else, look for your answer. See, where is your answer? It should be the last item on the problem. So go back and pick up the variable that you found. There's x, comma y, and write your answer as an ordered pair. That's the answer. Now, if we would do another problem, maybe what would happen is you would get the no solution or the overlapping lines. So we'll explore another method and see what happens, see if we can get one of those.